Let's have a look at an example of a model that we can use to make decisions. In this example, we look at the decision, shall we accept a customer order or not? In this example, we look at the company Aisha Furniture Manufacturing, and Aisha received 4 requests from customers to manufacture some furnitures during the next months. Now the problem is she cannot just simply accept all the customer orders because her resources to produce the customer orders are limited. And now she faces a problem to decide which of the orders she should accept. And what she wants to achieve is that the total contribution margin for these orders that she will accept, is maximal. In other words, she wants to earn as much money as possible from these 4 orders. This should be the criteria that we use to guide our decision making. Let's look at some available data. We can see this data, we can consider this data as given. For each order that Aisha manufactures, we require 2 machines. So one order is manufactured always on machine number 1 and machine number 2. We identify a machine by the letter J. And J can be the value 1 for machine number 1, or J can be value 2 for machine number 2. The capacity of a machine is indicated by the parameter Cj. C with the subscript J, and the capacity is limited. We write Cj, meaning the capacity of any machine, and our J can have the values 1 or 2, representing the 2 machines that we introduced. For the next months, where we want to produce the orders, the capacity of machine number 1 is 110 hours, and the capacity of machine number 2 is 90 hours. So how do we get to the capacity of the machine? First of all, we need to take into account how many hours per week are we working. Typically 40 hours per week is the working time. However, the machines require some maintenance, or maybe they are already booked to process some other orders. So these 110 hours and the 90 hours is just the capacity that is left that we can use to manufacture these 4 orders. Now Aisha has calculated the contribution margin. The contribution margin is indicated by U of I, and the contribution margin is basically the price that a customer is willing to pay for the order minus the variable cost that Aisha has to manufacture these orders. And we indicate one of the 4 orders by the letter I. So I, small I, can have the values 1, 2, 3, or 4. And for each order, there is 1 UI. Aisha has also determined how much capacity in hours, the machine capacity is given in hours. So here we also deal with capacity in hours. How much capacity Aij, the order I, requires on machine J. And this is given in the table below. So in the first column, the leftmost column, you have the orders 1 to 4 in each row. In the rightmost column, you have the contribution margin of each order. So if we if we accept order number 4, we will earn a contribution margin of 10,000 Omani Rial. Now, with respect to the capacity, if we accept order number 4 in the last row, then on machine number 1, you see here AI1, we need 20 hours, and on machine number 2, we need 50 hours. On the other hand, if we should accept order number 1, then we need 40 hours on machine number 2 and 30 hours on machine number 1. We always need to use machine 1 and 2 together. It is not either machine 1 or machine number 2. Yeah? These are different machines, and to perform one order, we need both machines. Yeah? For example, we are talking about wood processing, and one machine could be sawing, and the other could be polishing of wood or painting, for example. Now, this is the data that we are given. And now the question is, which of these 4 orders should we accept so that our total contribution margin is maximum and we do not exceed the capacity to produce these orders? Now we need to start building a model. First question, what are the objects that we need to consider in our model? Yeah, we were talking about machines, we were talking about orders, and we were talking about different relationships between the machine capacity and the orders. So we have here as objects that we should build our model about. We have 4 orders and 2 machines, and we have the relations between the orders and the machine capacity written here as in parentheses, round parentheses, ij. Yeah? So for each combination of an order I and a machine j, we have a value, and in this case, this is the required capacity to produce order I on machine j. This was shown in the table on the previous slide in column 2 and 4. Okay, next question that we need to find a clarification. What are the given attributes of these objects? Basically, this is the given data, the data that we already know about. Yeah? We call these data parameters, and in this example, we have the contribution margin. This is given for each order I. We have the available machine capacity, Cj, for each machine j. And we have the required capacity Aij of hours to produce order I on machine j. Since we have 4 orders and 2 machines, so we have 2 times 4, 8 values, 8 different values for Aij. Now, what are the wanted values for these objects? What are the endogenous values? What should be calculated by applying the model or with the help of this model? We call this decision variables. These are the decisions we want to make, and they are represented by our decision variables. And here our decision variable is for each order. We have 4 orders. For each order we want to decide, shall we accept this order or shall we reject this order? We model it in this example in the following way. We have a decision variable for each order, and this variable can have either the value 0, that means we reject the order, or this decision variable can have the value 1, which means we accept the order. Okay, let's move on. Now, what is the objective function? We already said that Aisha wants to maximize the total contribution margin, and the idea of an objective function is to measure how good our solution actually is. Yeah? We describe the goodness of a solution. With the help of the objective function, we can compare two solutions and decide which one is better. And technically, in the objective function, we always link some of the decision variables with some of the parameters of the model. There's always a link between some of the decision variables and some of the parameters of the model. Now we have some constraints. We already realized that we cannot accept all the four orders at the same time. This is the main reason why we need to have this model, and we call these constraints. Now we need to identify the relevant constraints, and again, a constraint is a link between some of the decision variables and the parameters of the model. We describe the dependencies among our decisions. And in this example, the constraint is that we are not allowed to exceed the capacity of a machine. We can only accept so and so many orders until we reach the capacity limit of a machine. It is possible to use a machine with a lower capacity, but we are not allowed to exceed the capacity of a machine. And we have two machines, so we have this constraint for machine number 1 and one for machine number 2. I wrote you down the model for this problem, for this order acceptance problem. And first of all, look at the 4 decision variables for each of the 4 orders, order 1, order 2, order 3, order 4. We can make the decision if we reject the order or if we accept the order. Accepting the order means the decision variable x has the value 1. So if we accept order number 3, then x3 will be 1, and if we reject all the other orders, then the x4, x2, x1 will be 0. Now, how to measure the goodness of this solution? We do this by using the following objective function. Let's get back to the given data, the contribution margin. Here in the rightmost column, for each order, a contribution margin was given. For example, for order number 1, 5,000 Omani Rial, for order number 4, 10,000 Omani Rial. And this is reflected in this objective function. If we accept order number 1, then x1 has the value 1, and we realize a contribution margin of 5,000. The same for the other 3 orders. And in the inequalities, in the formulas 2 and 3, we model our constraint. Inequality 2 models a constraint for machine number 1, the capacity constraint of machine number 1, and constraint number 3 models the capacity constraint of machine number 2. So let's have a look at the given data. This column represents the capacity requirements of machine number 1. So if we produce order 1, we need 30 hours of capacity on machine number 1. How is this reflected in the constraint? 30 hours of time is required if we manufacture order number 1. If we accept order number 2, then we need 20 more hours. If we accept order number 3, then we need 60 hours on machine number 1. And all the hours that we need for manufacturing need to be smaller or equal than the available hours, and we have 110 hours available, so we can only accept as many orders on machine number 1 if we stay below or at most equal to 110 hours. For machine number 2, exactly the same is happening. And now, in order to have a feasible solution, all the constraints need to be fulfilled. So it's not possible if we violate constraint number 2 and fulfill constraint number 3, it's still a problem. Yeah? All the constraints need to be fulfilled at the same time. Now let's look at some solutions. The first solution, a solution is described by values for the decision variables. We have 4 decision variables, so meaning a vector of 4 decision variables, and the values for this vector are 1, 0, 1, 0, meaning we accept orders number 1 and 3, and we reject orders number 2 and 4. Now, how to calculate the value of this solution? How do we calculate the value of the decision variable? We add 5,000 plus 2,000 is 7,000, and the other values are 0. So the value of the objective function is 7,000, and this is how we simply calculate the goodness of the solution. Now, you can easily see that this solution, where we accept all the 4 orders, has a higher goodness of the objective function because we accept all the orders. So we have 9,000, 11,000, 21,000 total contribution margin. This is clearly a better solution than the previous one. But what is wrong with this solution? If we replace the values, then it means we need 30 hours plus 20 hours is 50 hours plus 60 hours, 110 hours plus 20 hours, 130 hours. So this solution requires 130 hours on machine number 1, but we only have 110 hours available. And this tells us constraint number 2 is violated. We are not allowed. This solution is called infeasible. We are not allowed to implement this solution. Though we cannot use this solution because it violates our constraints. And that is how you can interpret a solution to such an optimization problem. Now you know from operations research that we have different algorithms to solve such a problem. This model that I showed you here is a binary linear optimization program. Most of the models you discussed in operations research are just called linear optimization models. Here's a special feature is to most operations research models, to most models from the operations research course, that we have here either the value 0 or the value 1 as a possible value for the decision variables. And in operations research, usually we have the full continuum, all values between 0 and 1 were acceptable. And because of this binary linear optimization, because of these binary variables, we cannot just apply the simplex algorithm. We need different algorithms to solve such a model. In this course Advanced Operations Research, we do not go into details, or we do not go into many details of the algorithms to actually solve these problems, because we focus on the modeling aspect, how to create these models, and we enter these models in the GAMS optimization software and solve these models via GAMS. And when we do that, we can find the optimal solution, which is given by the following vector, which means we reject order number 1, but we accept orders 2, 3, and 4. This is a feasible solution. Please check it for yourself. And the value of the objective function is 16,000 Omani Riyal. Well, that means Aisha should reject order number 1 and accept orders number 2, 3, and 4. And this will give her a feasible production plan. She has enough resources to manufacture these orders, and her contribution margin is the highest.